In the second part, we will talk about the linearization and differentials. Let me first make a very useful recall for you on what a linearization is and what is the importance of it. Okay, let's say that this is our function f of x, and let's consider the tangent line drawn at this point, okay? If I can make it. So this is a tangent line drawn at some particular point like this. And I need to try it again. I don't like it. So, okay, this is better. Let's say this point is 1, for example. And I want you to consider the image. Let's choose some image like here, 0.9. At this point, this is the image of our function, right? This is the value of this point, the value of function evaluated at 0.9, right? And you should also consider the image on this tangent line. And as you can see, they are really close. So what is this point? This point is f0.9, where this point on the pink line is the image on the tangent line. And this image is denoted as L of 0.9, L being the linearization function. So linearization function, as I explained in the lecture videos, are the same as the tangent line function, okay? The equation of the tangent line is the same as the equation of the linearization function. They are mainly the same thing, and the importance of linearization function is the following. As you noticed here, the exact value of the image, which is this one, f0.9, is so close to the value of linearization function. So what is the image on linearization function? It is L of 0.9. And the importance of linearization function is this. They are so close. So we will be using linearization function. So linearization function is used to approximate the exact value of functions. Exact value of f of x. Okay, this is the importance. In fact, this summarizes the importance of it and why they are so close to each other. As you see in the figure, the value on the graph is really close every time, no matter where you draw your tangent line. This will always the case. No matter where you draw it, the exact value will be so close to the value on the tangent line because of the fact that tangent line cannot move far away from the curve, right? Okay, after this useful recall for you, now we can deal with the next example. Look at the example. It says that find approximately the value of this thing. Normally, we cannot evaluate this value by hand. We need a calculator, right? We strongly need a calculator to find some value of it. By hand, it is impossible. But as we learned that the value of the linearization function gives us an approximation for the original function, we will use linearization function here. Okay, we will use the fact that the value of the function can be approximated by the value of the linearization function. So let's create the linearization of it. And there is a certain way to create the linearization function. Let me also write this certain way to our recall. So let me write linearization function of f of x at x equals a is created like this. F of a plus f prime of a x minus a. This is the way of creating it. This is the formula for it, okay? So what happens here in this particular case is L of 0.9 is computed as, okay, I will write such details in the solution of the next example. Okay, so we need to find the linearization of f of x at x equals, so here A is the point 1, okay, because we draw the tangent line at the point 1. And in this example, 0.9 is the point that is close to the point that you draw the tangent line, okay? So for your point A here, you need to choose the closest integer to this number. That closest integer will be the point that you draw your tangent line, okay? So the closest integer was 1 in our figure, and it will also be 1 in this particular example because 1 is the closest integer to 0.9, okay? Closest integer we should choose. By the way, what is our f of x here? You can guess your function by looking at this expression. We will be using f of x as x to the power x. And then to, okay, let me create some space here. And then to approximate the value of f 0.9, which is the value given in the statement like this, this is in fact the image of 0.9 under this function f of x, and we will be using L of 0.9 to approximate it, okay? This is the strategy, and to compute L of 0.9, you need to create your linearization function, and it is created by using the closest integer there. So let's use this construction now. L of x is f of 1 plus f prime of 1. You see, I am using 1 everywhere now. A is chosen to be 1. F of a, f prime of a, x minus a. This is the way of creating it. X minus 1. Okay, what is f of 1? Here is, your function is, you know, x to the power x function. So f of 1 is obviously 1. What is f prime of 1? Okay, this is 1, but what about this? To compute the image of your first derivative at 1, you need to find the first derivative of your function. So here, your function is x to the power x. And for such functions, you need to use logarithmic differentiation to find the first derivative. We covered this topic last week. Okay, now you can take the derivative. 1 over y times y prime is the derivative of the right-hand side with respect to x. And on the right-hand side, this can be written like that. You can use this property of a ln function. And now I have a product. I will apply product rule. 1 times ln x plus x times 1 over x is the derivative of ln x. So y prime is, this y should be sent to the right-hand side. So y is x to the power x. This is y times whatever you have on the right. Ln x plus 1. So this is the first derivative function. So we are ready now to compute the first derivative function at 1. So, sorry, what happened? Okay, so that's why f prime of 1 is 1 over 1, ln 1 plus 1, ln 1 is 0, so this is computed as 1, 2. That's why the linearization function is in fact like that. So it is what? I think after simplifying the constants, you obtain just x for your linearization function. Now we are ready to give an approximation for the desired value. Remember, we want to approximate this thing, which is the image of your function at 0.9. Sorry, this is exactly what it is. It is the image. And this is approximated by using the linearization function. And you see, it is much more easier to compute at 0.9. So the approximation is given as 0.9. You cannot compute this part, but On the right, by using the linearization function, you can easily compute it because it's a linear function. It is not complicated as this one. And the approximation for it is just 0.9. If you take your computer calculators right now and try to compute this strange number, you will find something really close to 0.9, which comes from the linearization function, okay? You can verify it by yourself. So it is like that. If you need some approximations for some strange computations, you will first construct the linearization function like that, and then you will find the image of that point on the linearization function, which will be the approximation for you. Can I move on? Any questions? Okay, let me move. Next example is so similar. I will just make a summary for you. Or maybe I can do some steps of it. Very similar one. You will just first get the function, and then you will start constructing its linearization and so on. Okay, what we want to do here. You can guess your function by looking at this expression. So the function should be, in this case, cube root of x, okay? And we want to find an approximation for this value, which is the exact value of your function evaluated at 8.2, and it is approximately the same as the value of the linearization function at the same point. So we will need to find or construct the linearization function at which point x equals a. What is a here? You need to draw the tangent line to your curve at the closest integer to this number. What is the closest integer to this one? The closest integer to 8.2 is obviously 8. 8. Okay, thank you. 8. So you will construct the linearization function of f of x, which is given as cube root of x at the point 8. Let's do that, okay? So L of x is constructed like f of 8 plus f prime of 8 x minus 8, right? Okay, what is f prime? F is cube root of x. F prime is, this is x to the power 1/3. So 1/3 comes down, you subtract 1 from the power. That's why f prime of 8 is 1/3, 8 to the power minus 2/3. So I think it is 1/12, right? And also we need the image of f8, it is 2. Let's insert these things. F of 8 is 2 plus f prime 8 is 1/12 x minus 8. This is our linearization function. Now, to give an approximation, I will, instead of computing from left, I will compute it from right by using the linearization function, and it will be the approximation for us. So what you see here for the linearization function, you can just write it in a simpler. Okay, let's leave it like this. And now approximation part. Okay, I want to approximate this thing, which is exactly this value, and it is approximately the same as L of 8.2, and it is computed by using this function. Instead of x, we will just insert 8.2. It goes like 2 plus 1/12, 8.2 minus 8. You see, instead of computing it from here, which is really strange and impossible to do by hand, you can just insert it here and you can easily do this linear computation, okay? So the result is, okay, let me write the result. Cube root of 8.2 is approximately the same as this number, 2 plus 1/60. I want to write it like this, okay? So this is the approximation obtained by evaluating on the linearization function. Any questions now?
No.
Is it clear, right? Okay,
Yes, teacher.
that's how you use linearization to approximate some strange values like this one or like this one in the first example. And we have a strong tool called linearization function to handle such approximations. Okay, next. In the next group of exercises, what we want to find. Find the linearization at a suitably chosen integer near x0. Okay. So for the 13, we would solve it. Our function is given as a to the power minus x, and we want to find linearization at, of which function of f of x e to the power minus x, at which point you need to choose the closest integer to this value. What is that? It is obviously 0, so let's create it. The linearization function of this f of x at 0 goes like that, f prime 0, x minus 0. F of x is given as e to the power minus x, so f of 0 is e to the power minus 0, so it is in fact 1. F prime of x, what is the first derivative of this function? Itself times the derivative of the power. That's why the first derivative evaluated at 0 is minus e to the power minus 0. So this is minus 1. Let's insert all these quantities. F of 0 is evaluated as 1 plus this is minus 1 x minus 0. So the linearization function is 1 minus x, right? This is our linearization. Now we will use it to approximate the value of f at this point. Okay, let's do that. So we want to approximate this thing, which is the value of f at the points minus 0.1. Sorry, there should be another minus here, right? Yeah, we are evaluating f at the point minus 0.1, like that. So it is approximately, this thing is easy to, very difficult to compute by hand. Instead, we will be using the linearization function to find an approximation, and it is much more easier than we think. So like this, minus, instead of x, I am inserting minus 0.1, so the result is 1.1. You see, it is that quick. Very quickly, we can approximate e to the power 0.1 by using the linearization function as 1.1. So this value, which is here, is approximately this value evaluated at the linearization function. Okay? And you can verify it by your calculators at home. Can I move on? Is this okay?
Yes.
Okay, let's move on. And I also want to solve this exercise. I think this is an important exercise for engineers, and I know that there are lots of engineers in my class, engineering students. So I also included it in your homework too, because I know that at some part of your professional professional lives as engineers, you will use this part somewhere. Okay, it says that show that the linearization of this function is given like that. It is a very easy question, but very useful one. To create the linearization function, you need first compute the first derivative of it, right? We will need it to construct the linearization function. How do you derivate this function? You take the power down, and then you subtract 1 from the power. We will also need f of 0, which is this quantity, so it is 1. We will also need f prime of 0, which goes like k times 1 plus 0 to the power k minus 1, and this is k. Okay, now I am ready to use all those things to construct the linearization function. Linearization function of f of x, which is this function given in the statement, at x equals 0 goes like f of 0, f prime of 0, x minus 0. Okay, we already computed f of 0 as 1. We already computed f prime of 0 as k, x minus 0. So you see, L of x is computed as 1 plus kx as desired here. So we proved that the linearization of this given function at this particular point is 1 plus kx. What does this mean? Instead of computing the images of, okay, it is given in the next example. So faster than a calculator. You know, the title gives you very nice hints. So you can compute the values of this function faster than a calculator by using its linearization. Let me show you how. Okay, this is our function, and it is approximated with the linearization function, and we computed its linearization function in this form, 1 plus kx. Now, I want to compute this, for example. What is that? It is, in fact, 1 plus, I want to write it in this form, 0.0002 to the power 50. You see, if I insert x as 0.002 and k as 50, then it exactly becomes this value. And now, what is the result of this expression? Again, you need a calculator, but you will see that computing it approximately from the right-hand side is faster than a calculator. How? It is 1 plus k is 50 and x is 0.002. You see, you can easily compute this linear approximation to find the result of this thing approximately. And this is, in fact, 1.01. You see, that fast you can compute the result approximately by using the linearization function. K is 50, x is like this. You can also do this one. Okay, let's do that. This is part A and part B. All you need to do is to write it in the form of 1 plus x to the power k. Okay, let me try to do that. So what do we have here? Cube root of 1.009. I want to write this in 1 plus x to the power k form. Okay, let's try to convert it. It is 1 plus 0.009 to the power. What is the power here? Can you tell me? It is 1 over 3. This was x here, this was k. And similarly, I obtained the same form. This is k. And now, time to insert this x and k in your linearization function. You know, linearization function, the result is given like that. So I will go like 1 plus k is 1/3, times x, 0.009. And the result is quickly computed as this value. So the result of this thing is approximately this by using linearization function. That's why the title of this exercise is faster than a calculator. Okay? So that's it. You use linearization function like this to approximate the values which are really difficult to compute by hand. And it is very useful and quick. Okay, any questions on that? So let me move on with the next part. Finally, we can talk about differentials now. What's a differential? It is here. I took this box from your lecture video, lecture notes. So to compute the differential of your function, all you need to do is to take okay, let's say y is f of x. Y is f of x. How do you compute dy over dx? Of course, you take the derivative of both sides. And from here, you can write dy alone on the left. Can you mute yourself if someone's microphone is on and it is disturbing me? Okay, it's better now. So you can write dy on the left alone, like f prime of x dx. So This is what we call as the differential. We call this expression as the differential dy. Okay, so that's the differential. Now let's compute some differentials. It is nothing but computing the first derivative of the given function and putting an extra times dx part on the right. Okay, you will just multiply the first derivative with the dx. That will give you the differential. Okay, for this one, dy is, take the derivative of ln. It goes like 1 over 1 x plus 1 over square root, like that. So this is the derivative of ln, whatever you see inside, times the derivative of the insider part. Now I will take the derivative of this quotient function. I will be applying quotient rule. Derivative of the numerator is 1 times the denominator minus derivative of the denominator. It's the square root function. So I take the derivative of the square root. Now times 1 comes from the derivative of insider part of the square root, and times x plus 1. Numerator stays the same, times the derivative of the denominator, divided by the square of the denominator. Here, this whole part comes from the derivative of the quotient. We applied quotient rule, okay? F prime g minus okay, let me just write like this. This is the derivative of the insider part. I will write it like that. This part comes from the derivative of this. X plus 1 square root of x minus 1 derivative. And to take the derivative of this, we apply the quotient rule. Remember? F prime g minus f g prime, f g prime divided by g squared. We apply this. Okay, and then at the end, you shouldn't forget to multiply it with dx. That's because you are computing dy, you need to multiply the derivative thing with dx. This is the differential of y. Is that okay? Okay, let's compute the differential of this thing. dy is this. This is shorter. How do you take the derivative of the exponential function? It is itself times the derivative of the power times dx, right? This is the complete differential of it. And we can also do this one. Again, exponential function. I don't touch anything. Itself times the derivative of the arctangent part. Arctangent x squared plus 1 derivative dx. So what is this derivative here? Let's compute this according to chain rule. And it goes like derivative of arctangent 1 over 1 plus whatever you see inside is squared here, and then you need to multiply with the derivative of this insider part. It is a square root function, so 1 over 2 times itself is the derivative of the square root, and then you move one step further. You need to multiply with the derivative of the most insider part. X squared plus 1 is derivated as 2x, and then at the end, you need to add your dx. So this is the complete differential of the given function. Okay. I think that's enough on computing differentials. It is nothing but taking the first derivative here. This is the first derivative of the given function times dx. It is nothing but taking the derivative multiplied with dx. Okay. If no questions, I want to move on. Let's move on. And finally, these two examples shows you how we use differentials in solving some examples. Okay, let's deal with this one. Here, what we have a tree. Okay, the diameter of a tree was 10 inch. This is the diameter of it. Okay, let's call RR, and this 10 inch is diameter of it. During the following year, the circumference increased 2 inches. Circumference, what's the circumference? Let's denote it by C. It is 2 pi r, okay, circumference. And it is given in the statement that in a year, the circumference increased 2 inch. 2 inch is a very small amount. And for a tree, in a year, the increase in the circumference would be very infinitesimal. It would be a very small amount, in very small amount. Such very small changes in functions, very infinitesimal changes, is denoted by the differentials. So what is given here by 2 inch is in fact the differential of this function, the circumference function. Okay? 2 inch is in fact the differential of the circumference. So its differential is computed as if your circumference is a function of depending on r. Okay, let me show you something here. If your circumference depends on r, just like here, its dc is computed as f prime of r dr, f prime being the derivative of f with respect to r. So what is it? What is the derivative of this expression with respect to r? It is 2 pi, and then you need to multiply it with dr2. So that's what we have. 2 inch, which is a very small change in circumference, very small changes on everything, is denoted by its differential. And 2 is equal to 2 pi dr. So from this line, you can solve for dr as 2 over 2 pi, and then after simplifying 2's, it is 1 over pi. In fact, this is the answer of the next question. Read the next question. About how much did the tree's diameter increase? So diameter is 2r, right? Sorry. So we need to compute 2dr. So the diameter increased. Small increase. Okay, let me put it in this way. I want to make the real life meaning of the differential very clear for you. So diameter is 2r. What is the relation between 2r and 2dr? How do you see this? This is what? This is a very small change. Small change in diameter. So what is it? This is asked in the question. How much did the tree's diameter increase in a year? It increased in a very small amount like this one. So 2 times 1 over pi. So your answer for how much the diameter increase is in fact 2dr. So it is 2 times 1 over pi. Okay. This is the answer for the first question, a very small change in diameter. Or you can say a very small increase, because in this question, it increases. Now, the second part. How much did the cross-section area increase? So this time, instead of diameter, this was the diameter. Now we need to deal with a cross-section of it. So the area of the cross-section, you see its cross-section here, okay? And its area is what? Area of the cross-section. Let's denote it by AR. Do you know how to compute the area of the disk? It is pi r square, right? And we are interested in the very small increase in this cross-sectional area. So I need to compute dA, just like we did here. Instead of 2, for diameter, we computed 2dr. Now, from A to dA, we should move, and we can easily do that. We can compute the differential of this function by taking the derivative of it with respect to r. So 2 pi r times dr, of course. Let's try to insert the values that we already know to compute this quantity. 2 pi, radius is 5, diameter is 10, so the radius is 5. And what is dr? It is computed here. dr is 1 over pi. So the result here is, you can simplify pi's and 10 inch. You see, dA is 10 inch much. In a year, the cross-sectional area increased 10 inch. So let me show this dr, dA in the figure so that you understand better. So after 1 year, the tree will grow a bit, right? It will grow like that. And the grow in the radius is denoted by dr. This part is dr, okay? And it is 1 over pi. Since there is also one other dr on the other side, 1 over pi, the small change in the diameter is in total 2 dr, so 2 times 1 over pi. And the change in the cross section is this much. And it is computed by computing the differential of the cross-sectional area. So this green shaded parts is in fact dA, which we computed as 10 inch. Okay? 10 inch square. So, sorry, the unit should be square for the area. Is that fine? So we use the differentials, dy, dc, dr. We use differentials to compute very small changes in the quantities, in the functions like that. Okay, any questions about change in diameter and about the change in the cross-sectional area like that? These are all computed by using the differentials. I think everything is clear now. Any questions? Okay, if no questions, I want to stop here. Thank you for listening.